So I want to address some of the homework problems, and first want to draw your attention to the fact that this was an amalgam of several previous assignments. So yeah, I am aware we are actually in spring 2021. So these are the suggested homework problems that I posted. The first thing you see is an RLC circuit problem. Now, we discussed the RLC. I'll just give a brief reminder. We had series R, SL, and 1 over SC. This represents a RLC circuit with a DC voltage source switched on at t equals 0, where the inductor and the capacitor had 0 initial conditions. And so if you recall, to find the current, we had V naught over S plus RI plus SLI plus 1 over SCI, and so I times 1 over SC plus SL plus R was minus V naught over S. And if we then solve for I as a function of S, sorry, that's plus, we get V naught over S times 1 over SC plus SL plus R. Multiplying the denominators together, we get V naught over 1 over C plus S squared L plus SR. And then if we put that in proper transfer function form, and this is important, and one of the reasons that are proper Laplace domain form, one of the reasons I'm going over this is so that you can see it's going to be V naught. And let's multiply everybody through, let's actually divide everybody through by L. So I got V naught over L in the numerator, and S squared plus S R over L plus 1 over LC. The reason to divide everybody by L is I want to get this S squared term, the highest order polynomial in the denominator, to have a coefficient of 1. So whether in an exam or in a project or just for your own homework write-ups or project write-ups, this is what we would call the proper form, where the denominator and the numerator are both rational functions, and the highest order term in the polynomial has a coefficient of 1. So that's the form that you want to put this in. You don't want any terms like this in your functions. All right, so now what we want to do is we want to look at the denominator, because it's what actually is going to determine the temporal response, and we want to find its poles. So S is going to equal minus R over L, using the quadratic formula here, square root of R over L squared minus 4 over LC all over 2, and if I bring the 2 up and under the radical sign, I get minus R over 2L plus or minus the square root of R over 2L squared minus 1 over LC. So now to the question at hand, we have, if we look at this denominator, or at this, this under the square root sign, when the square root of R over 2L squared minus 1 over LC is equal to 0, this is when the circuit is critically damped. So it doesn't matter what the input is, whether it's a voltage or a current. It doesn't matter what the functional form of the input is. The question of whether a circuit is underdamped, overdamped, or critically damped is a function only of the values of R, L, and C. So it is a natural response, meaning it's independent of the sources. The natural response of the system is it will have this characteristic based on its equivalent values of R, L, and C. of either being critically damped, overdamped, or underdamped. So at this point, what we want for the circuit to be critically damped, actually the first thing we're asked to do is design a circuit that will be underdamped, and then we'll try to make it critically damped. So first of all, let's figure out what would make it critically damped to kind of do the problem in reverse. That's when R over 2L squared is equal to 1 over LC. And so in that case, if L is 1 millihenry and C is 1 microfarad, at this point it's a matter of just taking R is 2 times 1 times 10 to the minus third. That's your 2L brought over. And then since I took the square root of both sides, I'll have times the square root of 1 over LC, which is 1 times 10 to the minus third. And C is 1 times 10 to the minus 6. So I'll let you do the math and get an actual answer for R. Okay, for underdamped, if we wanted to design an underdamped circuit, in that case, for underdamped, this radical, what's under the radical needs to be less than or equal to 0. So R over 2L, sorry, needs to be less than, not equal to. R over 2L squared is less than 1 over LC, which means basically whatever value you got for R up here, anything smaller will be an underdamped circuit. So as long as R is less than R for critically damped, then the circuit will be underdamped. The converse is also true if you choose R to be larger for a given inductor and capacitor value. If you choose R to be larger than the R value for the critically damped circuit, the circuit will be overdamped. Okay, at this point, you're asked to do some equivalent S-domain series and parallel combinations. So let me go to sort of the end of the document, and we'll add a work section here. So the first one, and I'll do it in terms of R, L, and C, and then you can just plug in the values. So when finding an equivalent impedance, you're not concerned about initial conditions. So when we go from R, L, and C, we just go to R, 1 over SC, and SL, because we don't have really initial conditions to worry about. And so we're looking at the equivalent impedance here. It's going to be a function of S. Everything is in series, so Z of S is R plus 1 over SC plus SL. And in order to find poles and zeros, I have to put that in a transfer function form. So finding a common denominator, I'm going to get an SCR plus 1 plus S squared L C divided by SC. So Z is, in the numerator, I'll have S squared, and I'm factoring out an LC. So I'll have S squared, and I'll factor it out from both numerator and denominator so that everything will cancel. So I've got S squared, and actually I don't have to do that. I could put my LC here. S squared plus S times R over L. Let's play with that for a minute. If I multiply that by SC, so I guess I need an R over LC, and then I need a plus 1 over LC over SC. Something looks a little wonky to me. Let's go back and do that algebra a little bit slower. Okay, so I'm good so far. I found the SC as a common denominator. Let's pull go ahead and pull an LC out of the numerator. That gives me S squared plus S. Oh, I see, I didn't cancel that C out. Just an algebra error. Now it looks right. And then in the denominator I have SC. And these two C's will cancel, but that doesn't matter because what I'm looking for is I'm looking for the poles and zeros of the transfer function, so of the impedance. So this is the impedance, Z of S. It's the equivalent impedance looking into the terminals. The zeros are the roots of the numerator. So it would be, once again, very similar to what we just did, minus R over L plus or minus the square root of R over L squared minus 4 over LC all over 2, and bringing up the 2, you can see from the previous example what that becomes. It's minus R over L, R over 2L, plus or minus the square root of R over 2L squared minus 1 over LC. Okay, so those are your zeros, and you have 2 of them, which you would expect because you have a second order polynomial in S. Your poles are the values of S that will make the denominator go to 0. And if you look in the denominator, we just have an S. So you have one pole at S equals 0. And that's going to become important to know what the poles and zeros are as we go to the next thing in class where we'll discuss Bode plots. All right, now let's look at the parallel combination. So for the parallel combination, do exactly the same thing. So this is SL, 1 over SCR, ZN. So there, let's put the inductor and capacitor impedance in parallel first. So we have 1 over SC times SL over 1 over SC plus SL. And if we do that, we get L over C. And then in the denominator, we get S squared LC plus 1 from multiplying through by SC. So that puts an SC in the numerator as well. So we will get SL, or SL, yeah, over, actually let me back up just a little bit. Let's just put that over a common denominator rather than trying to oversimplify. SC. Okay, so backing up a step, leave it in this form right here. Okay, now what we want to do is we want to factor out an LC in that denominator. So we've got L over C in the numerator. Factoring out an LC here, we're going to have S squared plus 1 over LC all over SL. And these two L's are going to cancel. So let's see, that was L over C in the numerator. And so this S here is going to come up to the numerator. SL over C times S squared plus 1 over LC. Now all that is the parallel combination of these two. So now what I have to do is I have to put that SL over C times S squared plus 1 over LC. I have to put that in parallel with R. At this point, it might have been easier to actually work this with numbers. I worked it with an R, L, and C so that it would be general, but sometimes working with numbers actually makes this a little simpler. So I'm going to stop here because I think I've given you a general idea of how you actually should go about this particular problem, and we want to move on so that these videos don't become too long. So let me see if I can insert. Why can I not insert anything? Okay. Okay, we'll leave that there, and let's come up and look at another problem that we can work. So, okay. All right, so let's look at, we can look at a transfer function problem, and we'll just review really quickly how to recognize what kind of filters we have here. There are four sort of well-known circuits: the low pass RC, the high pass RC, the low pass LC, and the high pass LC. And I will refer you to chapter 14, section 2 of your textbook for information on those filters. And I'm trying to see if they have anywhere in your textbook kind of a generic illustration. It doesn't look like they do. So that's kind of unfortunate. In this particular, these particular filters are both low pass, and so they have a transfer function that is of the form S over something. So, I'm sorry, in this particular one is R over L over S plus R over L. This one is RC, 1 over RC over S plus 1 over RC. Okay, so these are both low pass. They're passive because they only have RC and L, and they're first order because they only have a term, polynomial term with exponent of 1. So what we're asked is to create two different circuits that have the transfer function V out over Vn is 1000 over S plus 1000. So to address this little design problem here, what you need to do is, in case 1, for the first circuit, 1 over RC is 1000. And for the other circuit, so that would be this circuit. And in a design problem, you basically, usually the user or the designer has to choose one of the values. So that's why you refer to this appendix in your book, because that gives you common values of resistance and capacitance that you can purchase. So you have to choose one or the other off of what's available. As a general rule, capacitors are harder to size as far as purchase goes. So as a general rule, you look at what is available in a capacitor, and then so you choose your capacitor and then you solve for your resistor value. So the key to this problem is probably look up what's a commonly available capacitor value, and then ask yourself, is it reasonable to then calculate a resistor value that when I take 1 over RC, I'll get 1000. Inductors, you basically want 1 over, so that would be this circuit. For circuit B, you want R over L equal to 1000. Kind of the same thing, inductors purchase in particular sort of set values. So as a general rule, you would choose an inductor that you could either wind easily yourself or that you could find commercially available, and then solve for the resistor such that R over L equals 1000. What this circuit looks like is this circuit looks like a filter that has what we have defined as a cutoff frequency at 1000 radians per second. Now, I find a lot of confusion in the class about going back and forth from radians per second to hertz. So what you find is that when you calculate from R, L, and C values a transfer function, okay, and you have a transfer function that looks like either this or this, you're basically gonna have units in your frequency, in your cutoff frequency, of radians per second. So if you have a specification to design a filter in hertz, you have to convert hertz to radians per second. And if you see a transfer function like this, automatically this value of 1000 is given in radians per second. So if you want to know the cutoff frequency in hertz, you have to calculate that by taking omega and dividing by 2 pi to get hertz. So that's pretty standard. Okay, so we have in this second example a question that asks us to find the cutoff frequency in hertz for this given filter. So you know that our h of s for this filter, it's actually shown in the figure above, is r over l over s plus r over l. And r over l is 127 divided by 10 times 10 to the minus 3. So I think that should be 12,700 radians per second. And we're asked to find the cutoff frequency in hertz. So let me grab a calculator real quick. 12700 divided by 6.28 is 2022. So omega is 2 pi f. F is omega over 2 pi. So 12,700 radians per second divided by 2 pi radians per cycle gives us 2022 hertz. Okay, now we're asked to calculate h of j omega. So to find h of j omega, we basically substitute j omega for s. So h of j omega is r over l over j omega plus r over l. And omega c, as we know for this filter, is r over l. So going back to radians per second, at omega c, we'll have r over l over j times r over l plus r over l. And you can put some numbers in for r over l. In this case, you're calculating a ratio, and r over l is going to be common to every term, so it actually would factor out. Of both numerator and denominator, and you just have 1 over j plus 1. So in order to solve that, let me see if I can get myself some more space in here. I don't know if I can do that or not. No. Let's try this. For whatever reason, this just doesn't want to let me do this. Okay, so I have 1 over j plus 1. If you substitute instead for 0.2 omega, so h at 0.2 omega, h of j omega would be 1 over 0.2j plus 1. And at, what was the other one, 5 omega, you would substitute a 5. What you're trying to illustrate here is you're trying to illustrate that when the frequencies get low, this ratio is going to approach 1, and when the frequencies get high, the magnitude is going to go to 0. So just as a super quick review, and let's come down here to where I have blank space. As a super quick review, how would we find? So if we have h of j omega, we use the example where we have 0.2 j plus 1. So the magnitude of that is basically 1 over the square root of 1 squared plus 0.2 squared. Okay, and if you wanted to find the phase, which we're not really asking for, the phase of h is the angle whose tangent is 1 over the angle whose tangent is the imaginary part over the real part, 0.2 over 1. The angle whose tangent is 1 is what? Opposite over adjacent. Sorry, it is 1, oh, it is 0 over 1 because your imaginary component is 0. So this one is 0 degrees, and this one is some small angle where this is 0.2 and this is 1. So let me see if I can get that super quick. So 0.2 divided by 1, inverse tangent, I get 11.3 degrees, and those are both phase angles, and so to get the net phase angle, I bring the one in the denominator to the numerator, so angle minus 11.3. But usually people are mostly interested in, let me get this one, so 0.2 squared plus 1 square root of 1 over x. That doesn't look right. 1.04 square root 1 over x. So I get 0.98 here. So as you can see, where cutoff was at 1, as far as, because we factored out our r over l. So relative cutoff was at 1 times r over l, obviously. So we're at 0.2 here. We're at about 20% of cutoff, and we're getting pretty close to a gain of 1 on that filter. All right, so that's that one. I'm going to work one more, and then we'll stop the video. Here, you're basically asked, and we won't work this one, but I'll talk about it. You're basically asked to use a 5 millihenry inductor. You want to design a low-pass filter with a cutoff frequency of 1 kilohertz. So what that means is R over L is 2 pi times 1,000, or 6328. And you're given L, so R is 6328 times 5 times 10 to the minus 3. So gosh, I think if you do that, you get 31.4 ohms. I think that's right. I may be off by a decimal point. All right, now what you're asked to do is you're asked to connect a load. So the point of this problem, I'm sorry, I've got that backwards. The point of this problem is to see what happens when you come here. Here's your L and here's your R, and these numbers are the ones you just chose. And now what you're going to do is you're going to connect another resistor here, 270 ohms. And what you're asked to do is to find the corner or the cutoff frequency. This is called a loaded filter because basically what you did is you built this filter and then you hooked up a load to it. And so what you're interested in finding out is, how does the presence of a load impact the performance of the filter? Now this is actually an extremely physically significant problem because this is one of the reasons passive filters can become a problem, is that the load is going to draw current. This is why in most applications want to move to an op-amp filter where you have the protection of the infinite input impedance in the filter. So the situation is that what you would need to do here is you would need to calculate a parallel equivalent resistance, okay, which would give you some L and some R prime, which is the parallel equivalent of the R you calculated in part A and the 270 ohm load. And then given that, you recalculate L over R to find your new cutoff. And you remember that's in omega, so to get it in hertz, you would need to divide that by 2 pi. Okay? Now, problems 7 and 9 are basically exact duplicates of the previous two problems that we worked, except in that case, you're dealing with a cutoff frequency of 1 over RC. That's your omega cutoff. And so you basically are repeating exactly the same steps, except in an RC filter for a low pass, you take the output voltage across the capacitor, not across the inductor. Okay, I'm going to stop the video at this point because this primarily covers the kind of information that would be on your exam. So I think that this is sufficient. You've got a lot of videos to watch if you haven't watched the others, so I think this is sufficient. If you have any additional questions,